So welcome everyone to the January Data Facing Tracks call. Before we get right over to Bala, I want to very briefly remind everybody to take a look at the CARC website and be aware that upcoming calls and events are posted there on the website. I encourage you to visit the site and take a look at all the things we have to offer. There's a lot more going on outside the data facing track. Take a look at that site and have a look around. Today's call is going to be focused on Python for big data. And our presenter is Bala Desinghu. Bala is a senior scientist within the Office of Advanced Research Computing at Rutgers University, where he works with me providing research support for a huge range of disciplines across our multiple campuses. Before Bala joined us at Rutgers, he served as a research computing facilitator for the Open Science Grid at the Computation Institute at the University of Chicago. And as I mentioned, the topic for today is Python for big data. And with that, I'm going to hand it over to you, Bala.
Thank you, Galen. Let me share my screen. Google Chrome. Probably this, I think. So are you able to see my screen?
Yes.
Yes.
Thank you. Let me make it present more. So happy New Year, everyone. It's wonderful to give a presentation for the CARC meeting, data facing track. Title, you know the title now. So what I plan to do, so Python is a multipurpose language, all right? And then recently there are certain advancement in Python that helps us to do large-scale data analysis. Techniques like vectorization and then combined with distributed task executions can help us to do large-scale data analysis on multiple machines. And so the techniques that I'm going to show you today, the techniques and tools, they are very specific to Python. But the concepts, the general idea is kind of known for a long time. So if you are a Python user, the demo I'm going to show you, you can follow them easily. Even if you're not a Python user, you can follow the idea. And Python is really, easy language to follow. And you will see similar ideas and techniques in other languages. For example, the implementation of parallelism is common across many scripting languages, including MATLAB or Julia is different, but you will see all those details there. Okay, we all know about Python. It came out in 1990s, developed by Guido, and it's named after Monte Python. And it's one of the popular scripting language. So immediately it became popular, okay? People working in the web development, system programming, and network programming, and many other fields, they found Python to be really suitable and for their development. And recently, packages like TensorFlow, Keras, scikit-learn, all of them made Python to be a wonderful choice for data analysis and machine learning applications. There are several good reasons why Python is so popular. One of them is rapid development. If you have an idea, and then if you want to implement that idea in some programming model, if you take C or Java, and if you take Python, so Python is going to be really, really fast, okay? So if you take C and implement the idea, it may, let's say, it takes like 10 days and 10 pages of code. Then if you do the same thing with Python, it takes just one page and maybe one day, maybe less than that. So development is easy. Maintaining a short code is going to be easy. Distributing and working with their collaborators, all of them are going to be easy. So that's why, in industry like Google, Facebook, and Twitter, all the social media, they write their code, production codes in Python. So Python has its own limitations. Two of them are speed and memory. Python is great and fast for developing the code. At the same time, it is really slow when you try to run the code. So for numerical computation, it was not a great choice for a long time. And again, with memory, it is not so good in managing the memory. So the Python community was very active. They addressed these concerns through several methods. And these are some of the solutions outlined here. For the speed, NumPy, Numba, Dask, PySpark, Jython, Cython, MPI, Py, the list goes on and on. For memory management, it was not a very strong requirement because the data analysis era came a little later than the simulation period. So the speed was a big requirement for large-scale calculations. And then the big data came later. So now we have a very few solutions, or at least these are the solutions I found, like Dask is a Python framework. PySpark is actually a kind of interface to Spark, a distributed computing framework. Wax, I just found it, I have no idea. So for this presentation, we will be focusing on NumPy, Numba, and Dask. So what is big data, right? So we have, generally, people categorize the data complexity through these 4 V's: volume, velocity, variety, and veracity. Okay, so volume is the size, how big is the data, and velocity, now it has become so important. If you look at the smart devices and Internet of Things, a lot of data are coming in a very short period of time. Variety is like the type of data, like image files, text files, structured, unstructured, all those variety. And veracity is more about the usable and unusable usability of the data. Suppose if you have a data, let's say from medical records, and if the data has a lot of entries which you have to check or not legit, so that kind of thing. So you have to verify the data before modeling. So that's another dimension of complexity. So in this talk, we are mostly focused on the size, and this is the growth, like how the data grows with here. So nonlinear growth, okay, in zettabytes. So, okay, the volume is the focus of this current talk, right? But then, so the data could be in zettabyte size or petabyte. So one is the static data, like how much storage I need to store the data. And mostly, I'm keeping the data or transferring from one place to the another. They are kind of static. I'm not doing anything with them. They have their own challenges. The challenge that we want to address with Python is processing the data. So we want to get some insight about the data. So we have to process and extract the meaning out of it. So what that means, the data could be like in zettabyte, okay? But then for processing, I may need only few terabytes or gigabytes. Take for, say, for example, the digital sky survey, they collect the images of the sky every night, I think, around the globe. And that image has, and then they feed into a computer and gather the information about which are stars, which are planets, and which are galaxy, things like that. So if you look at only one tile at a time, so that's going to be really a tiny data, right? So you can process with multiple machine each frame. But for some reason, if you have to find the correlations between the images, then you need multiple frames. So more number of frames you need, that's going to demand more memory. So then the data size grows. The original data could be like in petabytes, right? So for my laptop, anything greater than 8 gigabyte is a big data. And if you take a Pittsburgh Supercomputing Center, they have Bridges 2 machine that offers something around 12 terabytes of memory per node. So then if you have a data more than that, you can manage there, right? HPE, they built a machine with 160 terabyte in 2017. That was the only news I found. I don't know what they did with that, but the news was everywhere, like HPC Wire and then some other blog post and everything. After that, if you look for the information, I don't know what they did with that. For most of the practical purposes, I would call 1 terabyte as the big data because many campus computing centers right now, the average memory is of 200 gigabytes. So if I have 1 terabyte, that's a big challenge. So the tools I want to show you will enable to process the data at least 5 times more than what your memory capacity can handle, or sometimes 10. So with one caution, so it won't work for all the cases. If the condition is very rigid, then you can do that. But in most of the cases, you can break down the data set and process them in chunks without losing the speed. And that's the idea. Well, this repetition here. We want to process the big data. There are a lot of tools out there, Spark and others, and we want to stick with Python because Python comes with great tools like visualization tools, data analysis tool, and everything. So we want to address this. Both for processing big data, both of them are limitations, like the speed and memory. So we want to attack the CPU and memory intensive computations with Python, okay? And there could be many other ways. So I am listing a very few approaches here. Data structure is very important. Okay, so that's an optimized data structure can go for a long can help you in many ways, and that is a very central theme, and that's what the Numpy came up with that. And it is not a new idea. It has been around in C and Fortran world for a long time. So Numpy implemented that. So that's an important one. So because of the data structure, with the good data structure, you can make the operations, the computing operation, vectorized, which means you can add 2 vectors, multiply 2 vectors directly, and avoid any loops. That's the idea. And just-in-time compilation is a kind of new idea. It came with Numba. It compiles a chunk of the code on the fly, and the compiled code is being used for vectorization and parallelization. So for both. I will walk you through some examples on that. But Numba is more like, I just want to show you how Numba was built on top of Numpy. The central thing is Dask. Okay, so it leverages distributed task executions. The Dask is great because it provides an API to NumPy, scikit-learn, PyTorch, TensorFlow, and it allows you to do parallelized computations on multiple nodes. For example, Numba limits you. NumPy is meant for single core. okay? And number takes you to the next level. It breaks the GIL, or global interpreter lock, that's a curse in Python. Actually, it was a beautiful thing when they wrote initially, but then later on for multiprocessing, it did not help. So number kind of breaks that barrier. And you can run Python code with number on single node, but using multiple CPUs and multi-threading. So Dask takes one more level higher. It will allow you to run your Python code on multiple nodes. And it gives it comes with some collections and wrapper for distributed machine learning. So particularly now, the machine learning tasks demand large computation and memory. So the Dask is an appropriate tool to attack both CPU and memory intensive computations. So what I will do, so that's the kind of an overview and what I will cover through the code examples. So basically these are like the tutorials I condensed into some demos, okay? The slides are available in the GitHub page, and the notebooks. You can just grab the notebook and follow them, or you can follow the slides. The slides are generated in HTML. I tried to do something different, but it did not work out. So I recommend you, if you want to watch on your own, I recommend you to follow the notebooks, okay? I'm going to run the demo. Not actually run, it's go through the demo with the HTML files. So let me switch to my slides. Okay, well, my internet connection is unstable. So any questions at this point? Okay, so can you see my the switched slide? Now I am showing NumPy slide.
Yes, looks good.
Okay, okay. Let me make it maybe full screen. Full screen, yeah. So NumPy is the first of its kind. What it does, it optimizes the Python execution. Basically, it's a C code. It provides an API to Python, and it's well optimized. There are two things with NumPy. One is the NumPy array, and the other is the universal function, which are vectorized functions. And then it provides fast linear algebra package and things like that, fast Fourier transform. So the image shows here very tiny. I could not adjust that. So the idea is that if you take a Python list it has like multiple elements, right? And then in the memory, they are scattered somewhere. Okay, the right-hand figure is the list. So there's a pointer pointing everywhere, right? So they are not continuous. And any Python object that has to find an element, it has to go through long path. So it's a conceptual diagram. So on the other hand, NumPy offers an array which is homogeneous, meaning that so array can have only integers or float, not mixed. But the list can have different types. That's okay with that. So that offers the flexibility, but then it becomes a bottleneck for performance. So the NumPy array has more metadata, like what type of array is that, and then it is completely indexed and everything is continuous. So it is a dense array. Okay, so this is the data structure that is very important. This allows for vector operation. So if I have an array, another array like this, and everything is indexed, if I want to add, say, I can do many other vector operation. Let's say I want to add. So I'm going to match 1 with 1, 2 with 2, 3 with 3, and then the addition is a kind of direct thing. On the other hand, with the list, it's a long process. okay? And so NumPy array, again, when you operate with NumPy array, there is no problem of checking the types. Types are static. With the list, with the Python list, the interpreter, we don't define the data type in Python. So what that means, so the interpreter has to check what every time when element, it has to read an element, it has to check, what is that type. So that conversion is not a big time. You won't notice it when you program, but if you have to do it lot many times as like a loop, that's going to cost a lot. So let me show you how Python list would work if I have two lists called A and B, okay, some values, all of them are integers, okay. I'm just adding these two, but it won't add, but rather it concatenates the two lists. So if I want to add them, I have to write a loop to add the elements. Now, if I look at the NumPy array, so okay, I'm declaring this to be an array. The syntax is very simple. We call that first we import NumPy as NP, right? And then NP is NumPy, short abbreviation for NumPy. And then we call NumPy array, and then we pass this list of values. Now, this is an array, and B is an array. And if I add both of them, I don't have to write a loop. They are just added together. So I get an answer directly. So it's a vector addition. So we can add two vectors in NumPy without a loop. So that's the vectorization. Now, what that means, let's compare the performance. So how fast or how slow is the vector operation with NumPy array versus the element-wise operation with list. Oops. So from the list, I can't directly do the addition. I have to write a function for that. So basically, I'm declaring two list values that's like 10,000 entries in each, and I'm adding them. And for that, I'm writing a function that does the loop. Okay. Now, if I compute the time, how much time it takes. So time it is a magic function in Jupyter. What it does, whatever operation I'm asking, here, it will do it for 1,000 times. It will run it for 1,000 times and get the average. So it's much more accurate. Okay. What we see is the average time is like 781 microsecond. Now, if I do the same thing with NumPy, this first of all, you can see the speed is like 3 microsecond, right? Much faster. And if you look at the code, it is much simpler. Instead of writing loops, I'm just directly, I declare the array, and then I'm just calling np add. Okay, just adding directly. The code is really simple. So, so it's about 250 times faster, but that's, it is supposed to be only 100 times faster, okay? For some cases, it can be faster. Some cases, it can be slightly slower. So where the speed is coming from? So if you look at the Intel website, they write the reason why they are after vectorization. So if you have a machine with 500 bit register, and it can hold up to 16 elements, okay, the numbers of 32-bit. And instead of one operation, the machine can do 16 operations with just one thing. So that's like 16 times faster, okay? But our code, ran like 200 times faster. But I know that the machine I used, it is again AVX 512, so it should be 16 times faster. So the reason is, so it is not only the vectorization, and underneath the code runs in the compiler, the compiled code, right? So there is no type conversion involved, the dynamic typing. So that is involved with Python. With NumPy, there is no, the types are static. That time is again saved. So overall, there's a huge saving there. And on top of that, NumPy codes are well optimized. The other thing, like I said, NumPy arrays are important. The other one is the universal functions. So what NumPy does, so we came across the universal function. The np.add is an universal function, which is completely vectorized. So the array is one thing where you have the dense array, the data representation, but you have to vectorize all your operations, and that's what the universal function does. So if I So here is another example. I don't want to go into the detail. So this is again finding an inverse of a vector. Again, the code is very simple. If I have a big vector like 1,000,000 entries, and then all I have to do is call the universal function np divide and then inverse of that. So I can immediately get the answer within 100 microseconds. And if I have to do it in a traditional pure Python way, I have to write a loop, and then that's going to take a longer time. Again, it's I think yeah, about 150 times slower. And then NumPy comes with several universal functions, exponentials and logarithms, and you have other functions like aggregates, computing mean, max, average, and you can do linear algebra. That's the most important one. If you want to diagonalize a matrix or find eigenvalues, so they are all there. So that's about NumPy. Okay, so NumPy is not the main focus, but it's because that's the basis of all the other methods, the modern methods. So it's good to understand, have an idea about that. So the question is, we used NumPy array and vectorized NumPy function, the universal functions. What if you have some operations that are not vectorized, right? So that's going to be slower. So if it is available in NumPy, that's great. If it is not available, what can we do? And that's where number is good. What I want is, I want to show number. Where is that view? Filter full screen. Okay, so number takes a very different approach. So if you give it chunk of code to number, and it will find a way to vectorize that function. That's one thing. The other thing is, if it is if it can be parallelized, it can parallelize the function. So it can do two things. And there are some extensive, detailed approaches, but I'm going to show the simplest one. You will see that if you remember, if you have done some MPI programming, so you have to design how to distribute the data, how to do what needs to be run in parallel, and then how you have to bring them for synchronization, all those things. But the number approach is really simple. It depends on, one is the LLVM library. LLVM library, what it does, it takes the code and compiles it, and it can make the code run faster with vectorization or parallelization. So that's the kind of approach, okay? And then the decorator is, that's a thing in Python. So what a decorator can do, it takes a function and it decorates. And we will see, we will use two decorators, vectorization and parallelization with just-in-time compiler approach. So the parallelization, what we are talking about now is about the threads. The diagram shows here difference between threads and processes. So what happens is the left-hand side is for multi-threads. So multi-threads are lightweight processes, and processes are like heavyweight compared to threads. And processes have their each processes, process got its own memory, own space, but threads share the memory. And that's where for the Python, what happens is Python has this global interpreter lock that prevents the threads to access the shared space. So the global interpreter lock is, so Python, when you type Python, Python executes through the interpreter. Now, so at the time, 1990s, there were not many, there were no multi-core machines. So, but then when they have multiple functions running in a loop, they may accidentally access the global address space. To avoid that, they created this lock, the interpreter lock for global variables, and that's the global interpreter lock. And it was a great thing at that time, and it helped running the Python interpreter smoothly. But now it is a bottleneck if we want to do multi-threading processes. So what Numba does, it takes the code. So this global interpreter lock exists if you are using the interpreter, right? If you kind of overcome that and go avoid this and then go directly to the compiled layer, then this doesn't exist. So that's the idea. Decorators, I will show you some examples. It'll be clear. Okay. So yeah, we have to import the libraries, Numba library, just the Numba. And if we want to use just-in-time compiler, we have to import that. What happened? So, okay. Yeah, so this is a very quick example I picked up. So the square root, finding a square root of a vector can be done vectorized already in NumPy. I'm going to pretend that this is not vectorized and then try to vectorize this using Numba, because so that you can compare, is it comparable to NumPy or is it bad, worse than NumPy? And if I do that for a million size vector, the square root, finding a square root takes like about 1 millisecond. And if I do that with traditional Python approach, it is going to be slower, right? And that's like 168 millisecond. Now, this is a Numba away, and this is the decorator, okay? All I have to do is whatever function we have to decorate it with the Numba function. If it is a vectorized decorator, you just add that. So what it does, it takes the underlying code from here till the return. This is a function, and whatever inside, it will compile and try to vectorize the code. And then same works for the parallelization. It is just simple as that. And if I time that, it is 800 microsecond, comparable to whatever NumPy did. In fact, it's slightly better than that. So the same, one is the vectorization, right? And the other is the parallelization. How can I parallelize a code? So Numpy does most of the vectorization. If anything misses, you can use Numba to do that. But how about parallelization? So Numpy is meant for only single core. In some cases, it can use threads, but that's not guaranteed. So the original intention of Numba was to take all the Numpy functions and make them multi-threaded so that you can scale. Like, if you have 10 cores, you are going to speed up Numpy by 10 times. So that was the idea. So it does it in a very automatic way. So here is an example, Monte Carlo pi estimate. So the idea is that if you have several independent calculations, they can be parallelized easily with the multi-threads. And here, on top of that, I have a serial code. So basically what it does, it generates some random numbers. And if the random number is within a circle, it is counted as kind of yes, it is inside the circle. And you take the ratio of the points inside the circle and then the total number of points. And that's the area of the circle. From there, you compute pi, okay? So here is the parallel version. So here's the parallel version. And then what you do is you use the decorator, the just-in-time decorator. And then you say no Python is equal to true. That means, you run this code not in Python mode. And yes, you want that to be parallelized. And then you want to remove the global interpreter lock. So just adding one line here. And the other thing is, instead of the range is a function in Python, and you can replace that with number prange. Even without that, it would work, but it is kind of highly recommended whenever if there is an number function, you use that number function, okay? So with that, here is the comparison for the serial execution. It is like 26 seconds. And for parallel execution, it is like about 0.5 second. So it is about 50 times faster, right? So where it comes from? So I am running this example on, I think I used it 28 core machine. So it has to be 28 times faster. And here it is slightly better than that. So at least, 20, it should be like 20 times faster. So that's the idea. So the more cores you have, the calculation will run faster. And you can tune the number of threads in Numba. So this is the variable number underscore num dot threads. You export this variable before you run the number calculation. So that's the way it works. Oh, I don't have the output here. So it is supposed to print that 28, but what I have. But the control on number of threads is not very clear here, right? But with the Dask, you have an explicit control over the number of threads and processes. So somebody, number can be used for vectorization and thread level parallelization, and it works also for GPU hardware. But in general, if you have to parallelize, you will see that Dask gives a much easier interface compared to Numba. Okay. So any questions so far? Let me see if there are any questions.
Yeah, there was one question in the chat related to Numba.
Okay. So Deep has a question. For the parallel version, can you tell Numba how many cores to use? Yeah, so okay, Deep, I just covered that. So the variable num underscore, what is that variable? I forgot the variable. This variable, number underscore num dot threads. So that's the one. Probably you wrote it like before I have flashed this slide.
Bala, there was one other question from the NumPy section that was posted in the call doc. And the question is, I didn't want you to get too far away from this question in case this is still relevant. In the first example, the list versus array addition, you attributed some of the plus 200x speed up to multi-threading. Is that true? And if so, what do you have to do? Do you have to do anything special to get NumPy to perform multi-threaded operations?
Oh, yeah, that's a very good question. In fact, I can only answer partially because, so NumPy is meant for single core machines, not for parallelism. I attributed the speed partially to multi-threading and partially to the typecasting. And some of the operations are with NumPy, they are multi-threaded, but not everything. I try to look at the exhaustive list. For example, the addition and dot products, they are multi-threaded. And then particularly if you compile that with the LAPACK library or Intel MKL libraries, they are super fast because the NumPy itself kind of multi-threaded for certain universal function operations, but not all of them. I try to gather a list. I don't have a list. So if somebody finds, that would be great. But some of them are multi-threaded. Okay, great. Let's move to Dask. Is this Dask? Yeah, Dask. So Dask, that's going to work for both CPU bound and memory bound problems. And you will see that it is strongly built on NumPy arrays, okay? And that's why NumPy arrays are very important. So Dask is good for CPU bound problems and for handling big data. So we are going to apply the same idea, whatever the distributed task executions work for managing large scale data. So we will see that, some examples of that. So one nice thing about Dask, it is kind of interface. It provides API to multiple other packages like NumPy, scikit-scilern, TensorFlow. So what that means, if you are working with, let's say, Keras or scikit-learn, okay, you can exist within, your code will be in the scikit-learn, and then you use the wrappers around the scikit-learn for scaling your calculation, whether for multiple nodes for speed up or for managing large data. So, but then, I have to warn you that, it's not everything is going to work automatically. Only some of the solutions exist. Everything is under active development, but some of them are well converged. Dask provides data collections, Dask Array, which is built on top of NumPy Array, Dask Data Frame, which is built on Pandas Data Frame, and Dask ML, which is a wrapper on scikit-learn machine learning tools. So you can just import all these tools once you install them. So two functions we have to learn in Dask. One is a delayed function. So basically what it does, it builds the graph. And then the compute function takes the graph and finds the resources and maps that. So it's basically a scheduler, takes the tasks and runs on these compute resources. So you will see that this is a common theme these days on many packages. For example, TensorFlow, right? It builds the graph before execution. And anyone from the Open Science Grid or Condor world, they know that for the distributed computing and workflow managers like Dagman and Pegasus, they build a graph, and then these graphs are mapped onto available machines. But the philosophy is kind of common, but the implementations are different. And this is the one allows go across multiple nodes. And then the same thing with Spark, Hadoop, all the distributed systems. So there are schedulers. A scheduler is the one that takes the graph and distributes onto available compute machines, right? There are several ways: thread-based scheduler, process, and the single thread. That's for mostly for debugging purpose. And then the distributed one, that's the most powerful one that allows you to go multiple nodes. And the threads is the default one. If you don't build, if you don't specify anything to the scheduler, it automatically tries to use multi-thread computation. So this is an example of how to build a distributed cluster. Okay, you just call this. There are two ways to build the cluster. One is the remote cluster, another is the local cluster. So I'm going to show only the local cluster. The remote is more meant for cloud computing. Suppose you want to build a cluster on the cloud from your laptop, that's what you do. I haven't tested that. So, but the local cluster would work most of the cases. Even if you want to do cloud computing, you can build a local cluster inside the machines you instantiated on the cloud. So what it does is you just say, how many workers you want, how many threads per worker you want, and that will, and then memory limit, and that would build a cluster. Now, if it is for single machine, it is really easy. But for multiple machine, you have to do some additional work, but the philosophy is the same thing. This is the one, once you build this, all the parallelism are taken care of. And if you, again, if you take the MPI example, you have to explicitly write, take this part of the code and execute on node 1, and this part goes to node 2, based on the rank. But here, the parallelism is like inbuilt. Once you build the machine, Dask would know how to map the tasks. You don't have to do any explicit writing. You don't have to say anything. What tasks should go where. So that's about a brief intro to Dask. So let me show how things work. So the Dask arrays. First, let me show you how the Dask arrays work. So what a Dask array does, Dask array is composed of multiple Numpy arrays. So that's why Numpy arrays are important. So underneath, a Dask array can hold multiple Numpy arrays. And then each Numpy array can be processed on different machines or different cores or different machines, however you want them to run. And it has built-in blocked algorithms to process many of the calculations. So that's how it works. So yeah, by the way, you can do that manually. So you can take a Numpy array, big array, and then split them into multiple Numpy arrays, and you can do some calculations. But then you have to coordinate all those things, right? So that's going to take a lot of time, and you have to scale it for different type of compute resources. So everything is taken care of by Dask in an automated fashion. So so this is how you import the required packages. So the memory profiler is a good one if you want to look at how much memory a function takes to run. There are two ways to run the memory profiler. One is within the code itself, and the other is like when you run externally and get a complete profile of that. So I'm going to use calling it inside the function for comparison. So let's take a Numpy array and then a Dask array. So first, so I'm going to create a size 20,000 cross 20,000 matrix. Okay, and what it does, it generates a random number based on normal distribution, and X is the matrix. And I want to compute the mean value for this matrix. It doesn't mean what's the actual number. Basically, it should produce just 10. 10 is the mean value, and this is the width of the distribution, I think. So it takes like 15 seconds. And the peak memory, it takes about 3 GB. Okay, and the number increment, meaning that is there any big jump in the memory demand? There is not a big jump, because whatever the peak memory consumed, that's the maximum. Once it loads everything, and that's it. Now, if you look at the same thing with the Dask array, so here it is a Numpy array, NP random, right? So here I'm using Dask array, DA. I already imported the Dask array, if you remember. Where is that slide? So I'm importing Dask array as DA, okay, and NumPy as NP. So that's the kind of shorthand. So here you see the peak memory is like 300, because I use the chunks here. So I'm breaking up the array into different size, 1,000. So that's like 20 times, 10 times smaller, right? So naturally, the memory requirement is also lessened. And not only that, the speed, if you compare the speed, it is much faster than the NumPy array. Why? Because by default, whatever I try to do here, I'm trying to compute the mean value of the matrix. And then it is going to parallelize, multi-thread all the operations. So that's faster. Again, it's a 28 cores. So if you compare, that's 14. So about, so it's not a perfect linear speed up, but it is a kind of good performance, relatively good performance. So the trick is that if you want to optimize the performance, you can change the chunks to 1,000, 2,000, variable chunks, and see what works. Ideally, you should match the number of chunks equal to the number of cores. That is going to, or number of resources. That is going to give you a big boost with your performance. So that's about Dask array. I don't want to drag too much into Dask array. Let me show you quickly. Oh, actually, we're out of time, like 1:55, right? Wow.
Yeah, we're getting right up there to the end of the hour.
End of the hour.
So there was a question about hybrid parallelization of these libraries. For example, a hybrid OpenMP MPI. Do you have any experience with hybridizing your parallelism of these libraries?
Oh, that's a great question. Again, that's a with OpenMP MPI. So that's the traditional approach, right? So the Dask is very similar to that. So you can do multi-process, multi-thread combined. But the thing is that you don't have to write any of that code. Once you build the cluster and use the Dask functions, whatever the underlying processes and threads, that should take care of that. It is a hybrid in that sense. But the difference is that the hybrid MPI and OpenMP, they can do a lot of data exchanges. Suppose, for example, if you run some calculation, similar to molecular dynamics or something, where you need to exchange the data very frequently, right? So there they win. If you compare the performance, the MPI would beat any of this, MPI or OpenMP. So they are like more rigorous calculations. But if the underlying tasks are independent, then Dask is very convenient to do. So it is more like you gain performance for certain types of calculations. So can I do like 2 more minutes and complete quickly the machine learning part? Just I want to show you quickly.
Please, go ahead.
Yeah, so I didn't keep track of the time.
Since we're at the very end of the hour, if anybody has a question, just go ahead and unmute and ask the question out loud.
Yeah. Okay, so the Dask arrays, and then there is the data frame. So they have the same idea. So the advantage is that if you want to do pre-processing with your data, then you have to use Dask array and data frames, which are very efficient. Okay, large scale data, like 10 times more than what you can do. So this is the delayed execution. I let you go, show the graph. Suppose if I have a large task, here I have an example function which does increment and decrement, and then I add at the end. If I use a sequential code, it will run one after another. So parallel should do this, right? And that's what it does in Dask. So this is the, for such 20 tasks. So here is the code that does, one after another. And then with the Dask, you get the parallelization without any trouble. Just you call the delayed function. So the idea is that, so Dask will order, here you don't define which task should go to which rank or anything. What you have is you are making a graph of executions using a delayed function. And when you call the compute, Dask will figure out which tasks should be parallelized, and it takes care of that. So the same idea, whatever the function, decrement, increment function, you can do that for machine learning or any other process. So that's the central idea here. So a quick overview of machine learning. So machine learning, what it does, so there are 2 types of compute problem, right? Dask can do certain ensemble-based method, and then it can take a data and chunk them, and then whatever we saw, like an array, it can take the data set and chunk them into multiple machines and do the training and prediction. And the other one is the incremental learning. So in the incremental learning, what happens is it will take one bunch of data and make the model trained, and then check it for, if the model is converged, then you can go for the additional data. So you can keep adding data and train your model, which is useful for online training and also for training large data. And you can use a Dask for something like hyperparameter optimization. That's very important. You can take a model and distribute the training on multiple machines and tune your hyperparameters. So with that, the examples are in the notebook. I let you go through that. So unfortunately, sorry, I could not cover the major part of the machine learning thing. I think it was really fun. But yeah, okay, maybe you can go through them and ask me if you have any questions.
Hey, Bala, there was one question from our Google Doc for the chunks option in Dask distributed. When you mentioned that the chunks should match the resources, what resources are you referring to? Memory, cores, nodes?
Oh, good question. So usually it is the number of cores. Say if I build a cluster of 10 nodes, each of them 32 cores. Okay, so that means 320 cores. So if I have well, I picked a wrong number. So if I have 300 cores, And then if my data size is like 30,000 entries, then each should be like, what is that, 300? So divided by that. So total size of the data divided by the number of cores. That's the approximate number, but you can go a little less, little higher. So if the task fails, Dask would reschedule the job, even the failed ones. So.
Okay, now with that, I think we really do need to end the call. So Bala, thank you very much, and thank you everybody. We had a really big turnout, a lot of great questions, and it's been a really good call. Thank you everybody for taking the time to tune in. And we don't have speakers lined up for February or March yet, but we're working on that. So stay tuned. Please visit the CARC website and pay attention to emails from this track, so you'll be aware when we do get somebody scheduled and ready for a presentation. Thanks, everybody. Bye-bye.
Thank you. Bye.
Bye, Bala. Thank you.
Bye. Thank you.